There. Algebra 1, we are in lesson 11. Today we are going to learn about how to choose an appropriate model for a situation when given data. Model in math class always means an expression or an equation of some sort. Okay, we're also going to determine the graphing windows, like the x and the y axis. What should we set them at? What increment? What's the maximum, etc. And then how to use exponential functions to model situations, either growth or decay functions. All right, so modeling exponential behavior. Wondering about windows. So here's a graph of a function f defined by f of x equals 400 times 0.2 to the x. So 0.2 is a number less than 1. That means we are decaying. 400 is our initial amount. And then the amount remaining is going to be 0.2 each period of time. All right, so identify the approximate graphing window shown. So shown, that means that my x-axis is from 0 to, I don't know, 40, let's see, 2, 4, 6, 8, 10, so 44. And then that goes up to 1,000, 1, 2, 3, 4, 5, 1,100. And that stinks. That's a terrible window. So to actually answer this question, we can say 0 is less than x is less than 44. So the x-axis goes from 0 to 44, and the y-axis goes from 0 to 1,100. Okay, that's terrible graphing window. That's the only data we see from that decay function. All right. We don't see any of this because it's all too small. We only see this, and we need this to be magnified. We need it to be a lot clearer. So let's suggest a new graphing window that would make the graph more informative or meaningful and make the graph less informative or meaningful. So to make it more informative or meaningful, I think our x-axis should be way zoomed in. So I would say from 0 to about 10. And then the y-axis, I'm absolutely sure what that should be. Because our maximum y value is 400, we should make it just a little bit bigger so that we can see everything. All right, so that would be much more informative. Less informative, I don't know, if we added some negatives, because it's never going to happen for this case. This answer could be almost anything. I don't know. Okay, and even here, if we didn't include some of the y values at the top or the bottom, like here, we're missing the maximum of 400, and we're missing everything from 0 to 10, and everything from 100 to 400. That's kind of silly. And here we have a negative 10, okay? Not helpful, and we're going way up to 80. Too high. Too high, too low, not low enough, not high enough. All right, and that's explaining my reasoning. Oh, sorry about that. All right, moving on. Beholding bounces. Okay, here are some measurements for the maximum height of a tennis ball after bouncing several times on a concrete surface. Okay, so bounce 0, the height is 150 centimeters. Bounce 1, so after bounce 1, it goes to 80. After bounce 2, to 43, etc. Think about that. All right, bounce 0, that means that some person is holding the tennis ball in their hand at time equals 0 and at a height of 150 centimeters. They drop it, it hits the ground, and bounces that back up. So time equals 1, it bounces up to 80 centimeters. Bounce, 43 centimeters. That's the bounce, not time. Sorry, it's the number of bounces. My bad. Let me erase that. So number of bounce is 0. After the number of bounces is 1. After the number of bounces is 2. Okay, this is what is going on. So that would be after the number of bounces equals 3. We're at 20. And that fourth bounce, I love how my graph or my picture is sort of leaning off to the side. This is 11, and then it just dribbles and rolls away, okay? Which is more appropriate for modeling the maximum height in centimeters of the tennis ball after n bounces? A linear function or an exponential function? Use data from the table to support your answer. Okay, if this were linear, the differences would be the same. If I subtracted these, all of the differences would be the same. So 80 minus 43, sorry, 80 minus 37 is 43. 150 minus 70 is 80. 80 minus 37 is 43. 43 minus 23, those are not consistent. The differences are not the same, therefore it's not linear. All of these numbers would have to be exactly the same amount for it to be linear. So let's do some division. So this is getting smaller. If I divide 80 divided by 150, 80 divided by 150 is 0.53. 43 divided by 80 is 0.53. That's 0.533, 0.538. 20 divided by 43, 0.465. 11 divided by 20, 0.55. Okay. These are called factors. I did 80 divided by 150. And then I did 43 divided by 80. And then 20 divided by 43. And then 11 divided by 20. These are factors. And they are pretty consistent. Therefore, it's exponential. It's exponential decay, but exponential. Okay, these are called differences. Not consistent. Therefore, not linear. Right? So, which is more appropriate for modeling the maximum height? Linear function or an exponential function? Definitely an exponential function. And supporting my answer would be all of this data right here. That's what I would write down if I were saying this is an exponential function and that is why. All right? Sorry about that. I'm back. Regulations say that a tennis ball dropped on concrete should rebound to a height between 53 and 58% of the height from which it is dropped. Does the tennis ball meet this requirement? Explain your reasoning. Okay, we did that math, and it meets the requirements here, here, and here. There we have a little bit of a problem. All right, so the first and second and fourth rebounds, so the first, second, and fourth rebounds are within range. Okay, but the third is not. Okay, the third rebound is less than 50%, falling out of the allowable range. So these are all between 53 to 55%. And this third one is about 47%. So it falls outside of the allowable range. Write an equation that models the bounce height h after n bounces for this tennis ball. So I know that expression, so I just need, equation. So we're going to say the height, which is a function of the bounces. We don't have to do that though, because I just said equation, not function. So the height equals our initial amount times our factor raised to the n. Now, what are we going to do about that factor? Okay, personally, I would take them and average them together. So I can say 0.533 plus 0.538 plus 0.465 plus 0.55, and then divide that by 4, and I get 0.52. So that's the value I'm going to use. Okay, anything within that 0.53 to 0.55, okay, that's going to work. All right. About how many bounces will it take before the rebound height of the tennis ball is less than 1 centimeter? Explain your reasoning. Well, we know that we can get to 4. I'm just going to guess. So what happens when n equals 5? So 150 times 0.52 raised to the 5th power, I have 5.7. N equals 6. 2.9. It's actually 3 if I round it correctly. N equals 7. Ooh, getting close. I have 1.5, so it's definitely going to be n equals 8. But let's get the value. 0.8. So the 8th bounce, we are less than 1 centimeter. And explaining my reasoning here is showing my work. Which is the bounciest of all? All right, so in class, I hope to get to this. If I see you guys and we have the time, your teacher will give you 3 different types of balls, a bouncy ball, etc. Your goal is to measure the rebound heights, model a relationship between the number of bounces and the heights, and compare the bounciness of the balls. All right, so ball 1, ball 2, and ball 3. All right, we're going to complete the table and make sure to note which ball goes with which column. We're going to figure out which appears to be the bounciest, and that would probably be the one that after the first bounce, it goes closest to its original height, right? And after the second bounce, it goes closest to the first bounce. That the bounces that doesn't decrease, your factor is the highest, okay? Or the largest will be the bounciest. I'll see if I can find a tennis ball. My dog may have chewed them all up, but we'll look. Okay, so that would be the bounciest, the factor that's the largest. Least bouncy, the factor that's the smallest. Okay, we're going to write equations for each one and explain how the equations could tell us which one is the most bouncy, and that's going to be the factor. I would say we would hold them to the same height for all three to help with consistency, okay? And it's going to be hard to figure out the heights after each bounce, but it'll be fun. We're going to do that. All right, are you ready for more? Email, are you ready? Lesson 11. Okay, email me. This is a good one. Half is bouncy. What's the equation? Okay. All right. And then 11.4. Behold more bounces. So let's look at 11.4. The table shows some heights of a ball after a certain number of bounces. Is the ball more or less bouncy than the tennis ball in the earlier task? Explain your reasoning. Well, let's do the division. Let's find out the factor. So we're getting smaller. So I want to do my division, 51.5 over 73.5. 51.5 divided by 73.5 is 0.70. And then 36 divided by 51.5 is 0.699. So 36 divided by 51.5 is also 0.70. So is this more bouncy or less bouncy? Well, our factor is bigger, so we are definitely more bouncy because the factor is 0.7, which is greater than the 0.52 of the tennis ball. From what height was the ball dropped? Explain or show your reasoning. So we're going to try to work backwards on this table. So if 0.7 remains each time, we need to get back to the beginning. All right? So what we really are going to say is, I'm going to work over here. My height is going to be equal to my initial, which I don't know, initial height times 0.7 to the n. Well, if I know my height was 73.5, I'm not sure what the height prior to that was, but 0.7 to the n. And that n, actually, we know that. Because if n was 2 here, so when n was 2, my height was 73.5. So 0.7 raised to the second power. I'm going to divide both sides. I'm writing over my words now. So 73.5 divided by that. My height prior to that was 150. Okay, so let's do the height prior to that. So 150 was my height. I'm not sure what that one was. When n was 1. So if I divide both sides by 0.7, we'll get the height prior to that. So the height is 214.2. 0.3. So 214.3. Just had to do some algebra to figure it out. Okay? And we used the equation that we came up with. So my height is height initial times 0.7 raised to the n. And actually this would be n minus 1, but that's okay. Let's call it height previous. So now we know that the height is 214.3 times 0.7 to the n. And explaining or showing the reasoning is the work that I showed up there. C number 2. Let's pick a graph. Which graph would be more appropriately represent the equation for h? Graph A or graph B? Okay, this is number 4. Well, this is not a linear function. Like this right here, sorry, not linear, but this is not a connected. This is, each bounce number has a very specific height. So we need a discrete graph in this case. So we're going to say graph B is a better representation of each height. And then will the nth bounce of this ball be lower than the nth bounce of the tennis ball? Explain your reasoning. No, the tennis ball's height was 150 times 0.52 to the n. This ball, I don't know what kind it is. The height is, it's bouncier, so it's going to always be higher than the tennis ball. It starts at a higher height, and it has more bounce. So every single bounce is going to be higher for this ball than the tennis ball, because we start at a higher starting height and we have more bounce. Lower height, less bounce. Okay, so this ball is bouncier and will always be higher than the tennis ball. And then we have our summary. Okay, this one is great. Talks about how to find the factors, which we've done. Talks about how to graph it. Really, I would pay more attention to the dots than the curvy line. Let's see, I'm skimming. That's it. Good job.